So, you're doing some difficult engineering schoolwork to prepare for an exam. As you frantically flip through your textbook notes, you cut your finger. Ouch! Engineering can be painful in more than one way. Your finger hurts and the cut bleeds a bit, but relatively quickly a scab forms and the bleeding ceases. How does our body stop us from bleeding in this way? Well, the key is coagulation. Coagulation is the process of blood changing from a liquid to a solid state. This process is not simple and involves multiple pathways and cascades, but before we get into the complicated stuff, we need to understand the role of platelets. Platelets are a component of our blood. They are almost like cells. They have mitochondria, a rough endoplasmic reticulum, and a Golgi apparatus, but they have no nucleus. Their half-life is about 8 to 12 days. Platelets have many receptors on their surface, which help regulate their activities. These can help platelets adhere to an injured tissue and aggregate into a clump. One of a platelet's most important functions is to form the platelet plug. The platelet plug helps temporarily seal the break in a vessel wall. This process consists of 4 steps. First, to form the platelet plug, contact must occur between the platelet receptors and the substrates from a damaged area. Second, activation and adhesion must occur, where the platelets change shape to cover the injury site and their adhesion receptors are activated. Thirdly, contraction occurs as the cytoskeleton contracts and pulls the wound together. Lastly, aggregation occurs and the platelet plug forms. All of these steps occur within 30 seconds. This leaves you plenty of time to continue studying and work on your exam. Yay. The platelet plug helps temporarily seal a broken vessel, but 2 more pathways are needed for a clot to form. These are the intrinsic and the extrinsic pathways. These pathways consist of a clotting cascade which contains many factors that activate each other. The first pathway is the extrinsic pathway. This pathway is activated by an external injury, such as a cut. The second pathway is the intrinsic pathway, which is activated by blood contact with a foreign surface. Both of these pathways work together to form the common pathway. The extrinsic pathway starts when the injured tissue releases tissue thromboplastin or tissue factor. Factor 7 and factor 10 are also released. These cause calcium to be secreted, and factor 10 activates as well as factor 5. This pathway then leads to the common pathway, where it will join with the intrinsic pathway's effects. The intrinsic pathway begins when blood contacts a foreign surface. Factor 12 activates, which activates factor 11 and secretes factor 9. These activate platelet phospholipids, factor 9, and secretes factor 10. Factor 8 is also activated. This pathway then joins with the extrinsic pathway via the common pathway. Both the intrinsic and the extrinsic pathways lead to activated factor 10 and factor 5. Calcium is released, causing prothrombin to be activated, releasing calcium and forming thrombin and fibrinogen. This releases calcium once more, causing fibrin monomer and stabilizing factor to be released. Calcium is finally released one more time to form fibrin threads. Calcium is key in this pathway in order for it to occur, as well as factor 10 as it joins both pathways. Thrombin is also key. So some important feedback loops that we should worry about. So in the extrinsic pathway, the feedback loop has to do with thrombin feeding back to factor 5. In the intrinsic pathway, thrombin feeds back to factor 5 and factor 8. So what does this have to do with biomaterials? Well, biomaterials can release an HMWK kallikrein complex. This complex can cleave kinins from the blood proteins. Kinins can cause pain and smooth muscle contraction. Thanks for watching.